Okay, let's just jump right in. Today's explainer is all about demystifying one of the absolute most profound mathematical concepts behind both human logic and artificial intelligence. I'm talking, of course, about Bayes' theorem. Now, I know that might sound a little intimidating, but at its core, it's really just the ultimate mathematical engine for how we learn about the world. It basically gives us this flawless logical framework for updating what we believe to be true whenever we stumble across new evidence.
To get started, we're going to look at a highly counterintuitive puzzle, straight out of Tom Mitchell's classic machine learning textbook. And honestly, this is going to completely break your standard intuition. So imagine you take a lab test for a really rare form of cancer. The lab tells you this test is 98% accurate, meaning, if you have the disease, it catches it 98% of the time. Then your doctor calls. Your result is positive. Cue the immediate panic, right? You're probably thinking you're 98% likely to have cancer, but actually, your brain is playing a massive trick on you right now.
Let's look at the raw data Mitchell presents. First up, the disease is rare. Only 0.8% of the entire population actually has it. Second, we've got our true positive rate. The test correctly identifies 98% of actual cases. Sounds good, right? But third, and honestly, this is the trap, the test has a 3% false positive rate. That literally means 3% of perfectly healthy people who take this test are going to be incorrectly told they have cancer. So here is the crucial, completely mind-bending point. If you test positive, the actual probability that you have the disease is not 98%, it's 21%. Yeah, an incredibly low 21%. Just think about that for a second. Even with a positive result from a highly accurate test, you are still overwhelmingly likely to be perfectly healthy. Why? Well, because the population of healthy people is just so incredibly massive compared to the tiny fraction of sick people. That 3% of the healthy group, it creates a way bigger pile of false positives than the tiny sick group creates true positives. It's pretty wild.
And when you actually plug these numbers into the equations, like in the textbook breakdown, you find that despite the positive test result, the maximum a posteriori or MAP hypothesis is still that the patient does not have cancer. The math is undeniable, yet almost everyone gets this wrong on their first try, mainly because we humans are just notoriously bad at intuitively calculating probability.
Section 1. Introducing Bayes' Theorem. So, to understand how our intuition was so spectacularly wrong there and how we can actually fix it, we need the formula. By definition, Bayes' theorem is a central theorem for reversing conditional probabilities to convert a prior distribution into a posterior distribution after observing data. I know, that sounds incredibly complex, but really it's just a profound intuitive framework for how we update our beliefs in the face of new evidence to arrive at a much better, more accurate understanding of reality. Think of it as basically the mathematical formula for open-mindedness.
Christopher M. Bishop elegantly sums this up in his book, Pattern Recognition and Machine Learning. He notes that your updated belief, your posterior, is proportional to the new evidence you just saw, multiplied by what you already knew before you saw it. You're never just looking at new evidence in a vacuum, right? You always have to weigh it against your existing baseline of reality.
Section 2. Prior, likelihood, and posterior.
Let's break down those three mathematical pillars by simply framing them as the process of learning. You start with a prior assumption. That's your baseline knowledge of the world. Then you observe new data, and that acts as your likelihood, basically asking how probable is this new data if your initial assumption is actually true. Finally, you mathematically combine them to output a posterior. That is your newly updated, refined belief. And the really beautiful part about all this? Today's posterior just becomes tomorrow's prior as you continue to learn and go through life.
Now, before we move on, it's super important to contrast this Bayesian view, which treats probability as a subjective degree of belief that's constantly updating, against the classical frequentist view. The frequentist perspective sees probability strictly as long-term relative frequencies, like flipping a coin an infinite number of times. But the Bayesian approach, it allows us to assign probability to things that don't even have long-term frequencies, like figuring out whether a specific patient has a disease right now based on a mix of their unique history and just a single test result.
Section 3. The probabilistic inverse.
Okay, so why did our brains fail so badly at that medical diagnosis puzzle earlier? It all comes down to the probabilistic inverse. Reversing conditional probabilities means you have to realize that the probability of x given y is fundamentally wildly different from the probability of y given x. For example, the probability that you have an umbrella given that it's raining is quite high, but the probability that it's raining given that you are holding an umbrella, not necessarily as high. Maybe you just bought it at the store. In our puzzle, the probability of a positive test given you have cancer is 98%, but the probability that you have cancer given a positive test is only 21%. They are completely different questions.
And the exact reason that cancer probability remains so shockingly low is because of the prior. Because the prior probability of actually having the cancer in the general population was that incredibly tiny 0.8%, it acts like this massive heavy anchor. It literally drags down the 98% likelihood of the test. Bayes' theorem mathematically forces you to respect the rarity of the disease before you're ever allowed to interpret the new evidence of the test.
Section 4. Updating beliefs with data.
Which brings us nicely to how modern artificial intelligence actually learns. Because algorithms don't have human cognitive biases, they can apply Bayes' theorem flawlessly at scale. When you look at the evolution of posterior probabilities as a machine learning model accumulates data, you can really see this process in action. Initially, before any data is observed, the algorithm assigns equal probability to several different hypotheses. But as it processes more and more data, those probabilities dramatically shift.
Notice how the exact moment the training data completely contradicts a hypothesis, its posterior probability instantly drops to 0. Boom, it's just completely eliminated from the algorithm's consideration. Meanwhile, the remaining hypotheses that are still consistent get to share all that leftover probability mass. They grow taller and taller until the algorithm finally homes in on the single undeniable truth.
Section 5. Scaling to machine learning.
It's this constant feedback loop, updating priors into posteriors, that allows algorithms to scale up and solve incredibly complex problems, like, say, a self-driving car determining if a shadow is actually a pedestrian. By constantly crunching Bayes' theorem through complex equations, an algorithm rapidly searches through a massive, multi-dimensional hypothesis space to find that maximum a posteriori or MAP hypothesis. It's essentially doing exactly what our human brains failed to do with that cancer test puzzle, but it's doing it millions of times per second.
Section 6. The Bayesian takeaway.
So we've seen how Bayes' theorem transforms what looks like a dry statistical formula into the very engine of machine learning and logical deduction. It truly is the gold standard for how to change your mind when presented with new facts. So I want to leave you with this. If cutting-edge AI algorithms rigorously update their beliefs by mathematically weighing their priors against new evidence, shouldn't we be asking ourselves how our own deeply held priors are impacting our daily decision-making? The next time you hear a compelling piece of new evidence, ask yourself, are you actually updating your posterior, or is a stubborn prior just anchoring you to the past?